Hey everyone, welcome back to another lecture on fluid mechanics. Let's take a look at what we're going to talk about in this video. In this video, we're going to talk about the flow in conduits, or pipes. We're going to discuss, number one, what is a conduit? We'll talk about the effect of Reynolds number, how we classify flow, as well as the Darcy-Weisbach friction factor equation, and discuss roughness in pipes and how we calculate the friction factor so we can calculate the head loss in these conduits. So first off, what is a conduit? A conduit is basically just any duct, tube, pipe, or any network that's transporting a fluid from one place to another. That can include HVAC systems in a building, like air, or it can include geothermal pipes out in Iceland that move geothermal fluid from a power plant all the way to the local city. One distinction we do have to make is the difference between open channel flow and conduit flow. For it to be conduit flow, the pipe has to be fully filled with the particular fluid. If you had a pipe or system that was only halfway filled with the fluid, that would be considered open channel flow, and that's not going to be something that we talk about in this lecture. Now, there's lots of cool examples of conduits and pipe networks all around the world, and one of the coolest ones that I think of is the Trans-Alaska Pipeline. Now, this pipeline transports oil from Alaska all the way down into the continental United States. You can see that there's over 800 miles of pipes, which is kind of a crazy amount when you really think about it. The pipe diameter of this whole pipe is about 1.2 meters. And you could imagine, as we've talked about, because there's going to be the friction in the pipe, because there's ups and downs of the terrain, you're going to need lots of energy to move the fluid from one place to the other. And across this 800 miles, there's actually 44 different pumps that pressurize the oil to actually get it to where you need it to go. Now, if you were an engineer and you were designing an advanced pipe system like this that spans countless miles, you're going to have to take into account friction. The things that are going to be most important to you are to, number one, determine if the flow in the pipe is laminar or turbulent, and to, number two, determine the pipe size and the roughness, which essentially translates to the internal friction related to the material that you're choosing. You can imagine if you have a smooth pipe versus a very rough and corroded pipe, the flow might be more laminar, more turbulent, or you'll have more viscous effects of drag in the fluid itself. So let's take a look at a little bit how we do this. You may recall that we've introduced the concept of Reynolds number already. Essentially, this is a dimensionless coefficient that helps us understand whether flow in a pipe is laminar or if flow in the pipe is turbulent. In Reynolds' experiment, what he did was he injected a stream of kind of colored dye into a flowing fluid in a pipe. And what he measured and saw was that at low discharge, the stream stayed more or less intact, and you could see the line of colored fluid as it flowed through the pipe. But as you increase the rate of discharge in the pipe, you saw greater and greater turbulence throughout the system and greater dispersion of the fluid, which should make some sense. Reynolds number can be calculated using the equation shown here, and you can see that using different fluid mechanics iterations of formula, we can make lots of different forms of the Reynolds number equation. The most simple one is the one that's right here, which is our VD over kinematic viscosity. Essentially, this just relates to the velocity of flow in the pipe, the diameter of the pipe, and the viscosity of the fluid that you're working with. If we use the relationship and understanding that density over mu is actually equal to kinematic viscosity, then we can substitute the formula there. And you can see the other formats there. We're using essentially flow rate instead of velocity, or mass flow rate as well. At the end of the day, all that really matters to us is that we're using this Reynolds number and the qualities of the system that we're given to calculate whether we have laminar flow or turbulent flow, which is going to help us understand the head loss in the pipe system better. The two things that we could probably point out here that should make some sense is that higher speeds are going to increase the likelihood for turbulence, and that's what we can see right here. And the other thing is that we can see that larger diameters are also going to give more room for turbulence to form. So the idea is really just that the faster you've got the fluid flowing and the larger the diameter of the pipe, the more room you have for the turbulence to actually form. And you can see that represented in our equations. So, as we've discussed before, Reynolds number, if it's less than or equal to 2000, will yield laminar flow. Over 3000 will be turbulent flow. and somewhere in the middle is a little bit unpredictable. Another concept that we'll consider is what's called developing/fully developed flow. Essentially what happens in this is that when you've got fluid flowing from one pipe into another pipe, there's going to be an area right around here where we've got what's called this entry length, or kind of the length of the pipe that it takes the fluid to really form into the flow that it's going to have throughout the rest of the particular system. What we can see for entry length is we have these two formulae right here. They're going to depend on whether our flow is laminar or turbulent. So if we wanted to calculate the Reynolds number and figure out whether our flow is laminar or turbulent, we can then look at the entrance length to see exactly what effect we might have on the fluid flowing in. Let's do an example now and calculate the entrance length of a system with a fluid flowing in a pipe. Let's take a look at this example right here. The question asks us to consider a fluid flowing in a round tube of length 1 meter and diameter 5 millimeters. We're asked to classify the flow as laminar or turbulent and to calculate the entrance length for two different fluids. The first being air at 50 degrees Celsius, speed of 12 meters per second, and the second fluid being water at 15 degrees Celsius with a mass flow rate of m dot equals 8 grams per second. So we're given some values down here for air and for water related to their values of kinematic viscosity, and we're going to use that information to actually calculate everything that we need to do. So let's take a look and figure out how we're going to do this. Step number 1 is going to be to solve for Reynolds number so we can determine whether the flow is laminar or turbulent. Once we have that, we can use our relationship for entrance length and solve for the rest. So let's first solve for Reynolds number for the air and then the water. So we know that Reynolds number is equal to V times D over kinematic viscosity. Now in this particular example, we were given the velocity of the air. We were told that the velocity was 12 meters per second. We were told that the diameter of the pipe is actually given as 5 millimeters. So 5 millimeters times 1 meter over 1,000 millimeters is our diameter conversion, and we'll divide that by the kinematic viscosity for air, which we can see as 1.79 times 10 to the negative 5th meters squared per second. So what you can see here as we calculate our Reynolds number for air is 3,350. And because this value is greater than 3,000, we can classify the flow as being turbulent. Now, because the flow is turbulent, what we're going to do is use the relationship we saw on the previous slide for the entrance length for turbulent fluid flow. So when the flow is turbulent, we use the equation for entrance length. The entrance length is equal to 50 times the diameter. 50 times the diameter in this case will be 50 times the diameter, which is 5 millimeters, or, as we calculated earlier, 0.005 meters. And we get that the entrance length is equal to 0.25 meters. For our water in this example, we were given mass flow rate rather than a velocity. So what we'll do is we'll go back to the earlier page, we'll look at our equation for Reynolds number with mass flow rate, and we'll write that one down and plug everything in. We can see from earlier that our Reynolds number is equal to, in this case, 4 times m dot divided by pi times the diameter times viscosity. So we're actually given all of these values here in the problem, so we're going to use those to solve for Reynolds number now. We plug everything in, we'll have the value of 4 times m dot, which we were given in this problem as 8 grams per second. We're going to want that to be in kilograms per second, so we're going to say 8 grams per second times 1 kilogram over 1,000 grams. Then what we do is we're going to divide that by pi times the diameter, which is, in this case, the same as before, 5 millimeters. so times 0.005 meters, times the viscosity value for water, which we were given 15 degrees Celsius, which is 1.14 times 10 to the negative third newtons times seconds per meter squared. So what we get for Reynolds number here for our water is that the Reynolds number for our water is equal to 1,787, which that is actually less than our threshold for 2,000, so that means that our flow is laminar. Now that we know we have laminar flow, we'll use our equation for entrance length and solve for that. So that's our second step. For laminar flow, our equation for entrance length is going to be given by the entrance length being equal to 0.05 times the Reynolds number times the diameter of our pipe. So if we plug in all the numbers we now have, we get that 0.05 times the Reynolds number of 1787 times the diameter of the pipe, which is 0.005 meters. We get that our entrance length is equal to 0.447 meters. One thing we can observe about the entrance length equation is that as our Reynolds number gets higher, our entrance length will also get higher as well. This should make some sense because as the flow is turbulent, it's going to take a little bit longer for that flow to organize itself and enter into the pipe system. What we also see is that our entrance length is dependent upon diameter. And when diameter is brought to the other side, when the diameter goes up, the entrance length also goes up. This is because the larger the pipe is, the more time it takes for the fluid to spread out. You've got greater likelihood for turbulence in a larger diameter system as well anyway. So in the end, the diameter and the Reynolds number both affect the entrance length. So that's our example on entrance length, and let's look at a couple other topics. In looking at fluid flow in conduits, one of the things that's going to matter quite a bit is the pipe itself. In the pipe nomenclature naming, you can see that there is an NPS, or nominal pipe size, which gives you the size of the pipe in inches, at least in this particular table right here. Now, it's a little bit tricky because you might see the first example, the nominal pipe size is 1/2 inch. What that actually tells you is that the outer diameter of that pipe, standardized system, is 0.84 inches. And there's actually this weird topic called schedule. Now the schedule is essentially telling you how thick the walls of the pipe are. So you can see for a Schedule 40 pipe, wall thickness is 0.109, and for a Schedule 80 pipe, the wall thickness has increased to 0.147. You can see for these two schedules, you've also got an inner diameter for the Schedule 40 and the Schedule 80. And you can see that as the pipe gets thicker, the wall thickness, the inner diameter goes down as well. So no big deal there. The main equation, the main takeaway is that really you just want to look at the inner diameter of the pipe because that's going to be the part that actually is affecting your fluid flow. In these next slides, what we're going to do is discuss and kind of derive the equation for head loss in a pipe. And we've already introduced it in the past, but we never actually derived where it came from. Now, you don't need to copy this down or pay really that much attention to it. It's really just a derivation that's going to explain to you where our head loss equals friction times L over D times V squared over 2G comes from. So what we do is we apply the energy equation to a pipe that's at an incline. We can see that if we've got constant fluid flow, the velocity on the left and the velocity on the right side of the pipe is going to remain constant, and we have only pressure and elevation in our energy equation, as well as head loss. What we also want to do is we want to sum the forces in the pipe, because at the end of the day, what we're trying to find is the force of friction acting along the length of our pipe, more or less. If we look at this and we see what forces are acting on the pipe, we see we've got pressure forces on the left and right side. We've also got the weight of the fluid acting down and to the left, and we've also got the shear force, which is the internal fluidic friction of the system. When you sum the forces on a pipe, you're going to have the pressure force on either side of the pipe on the left and along the right side, and that's going to be multiplied by the area. So that is our force kind of going up and the force going down. We do have that pressure change as the pipe changes its elevation. The other thing that we're also going to see is that we have shear force in the pipe, which is related to the fluidic friction of the particles rubbing together. This is something we introduced way back in the beginning of the class, but you can see that's based on tau, the diameter, and overall length of the pipe that the fluid is flowing in. So we've got that as well. The last little bit you'd have to factor into your sum of the forces equation would be the weight of the fluid, which you can see is our gamma times the cross-sectional area of the pipe times the length of the pipe times sine alpha, because we're looking at a sum of the forces along the axes that is in the direction of the pipe this way. Now you may remember from earlier in the class, fluid velocity changes as a function of where in the pipe's cross-section you are. We explained that maximum velocity usually occurs right in the middle of the pipe, and we have smaller and smaller velocities as you get closer to the edge of the pipe. The other concept we have to take into account is the fact that shear stress is also a function of pipe diameter and where you are in the pipe. As you can see here, the shear stress increases as you get closer to the walls. And this matches our expectations because we discussed earlier in the class the fluidic friction is highest when the fluid is touching the wall of its container. That's where you're going to have the most friction, and that's where we've also explained you have what's called the no-slip condition. We're essentially assuming that the velocity is zero because you've got maximum stopping force or friction force located at that wall. Now, when you combine these equations and you simplify things a little bit, it's a lot of algebra, you end up getting the equation shown right here for head loss. It's going to be a function, as we've said, of the length and diameter of the pipe, as well as this little bit in the middle, which is essentially a function of the shear stress and how fast the fluid is flowing. We multiply that by the 1/2 rho v squared, which is kind of like our energy term, and at the end of the day, we get exactly what we would expect. The only wrinkle in this formula you might see is this little bit in the middle, and what that is actually going to be how we calculate this friction factor F. Earlier in the class, or at least up to this point, in previous examples, we've only given you the value of F. You've never had to calculate it or figure it out on your own. But as we move a little bit further, we're now going to calculate how you get this F using, not this equation, because that looks kind of crazy, but we're going to do that using a couple other methods. So the main takeaway here is really that we've got our equation for head loss due to friction in the pipe, and we now have a way to conceptualize where the friction factor is coming from. The friction factor F is dimensionless, L over D is also dimensionless, and V squared over 2G is going to be in meters, and that's why it's called head loss. It's not because whoosh, you're losing your head, but rather because you are actually dropping in distance. Just like with entrance length, the friction factor is going to also depend on whether flow in the pipe is laminar or flow in the pipe is turbulent. Now, when flow in the pipe is laminar, you can actually calculate friction factor using the equation shown right here. Essentially, what will happen is when flow in the pipe is laminar, you plug in a couple different things and you see that the Reynolds number underneath the value of 64 is actually going to lead you to the friction factor. Very simple. So if you're doing a problem and it asks you to solve for friction factor and a laminar pipe, well, boom, you've got a super easy equation right there. So what are you going to calculate friction factor when you've got the pipe is turbulent? You're actually going to need two pieces of information. You're going to need the Reynolds number, and you're also going to need what's called the roughness coefficient. Now, the pipe roughness is affected primarily by the material of the pipe, and you can see that shown right over here on the left. Oops. You can see that the pipe roughness coefficient for all these different materials varies. So if we look here, some of the rougher materials, for example, like concrete, has a very high coefficient, relatively speaking, for a friction factor when we compare that to something that's a lot more smooth, like, for example, glass or plastic. When a pipe is considered smooth, we say that the value of the sand roughness coefficient is actually 0. Now, what is all of this really related to? So what do you do if the flow is not laminar? Now, to calculate the friction factor when flow is not laminar, you're actually going to need two pieces of information. Number one, you're going to need Reynolds number, and number two, you're going to need what's called this roughness coefficient, or how rough the material of the pipe is. Essentially, the roughness coefficient is how many bumps, or how, rough the pipe actually is. So you can see that the higher the roughness coefficient, the more notches and more chances to develop turbulence and kind of lose energy are. You can see that this is going to be primarily material dependent, and for things like concrete, which we know if we fall down and scrape our knee is quite rough, that actually has a roughness coefficient of 0.323, whereas something that's smooth like glass, plastic, or even PVC pipe, we actually qualify that as just having a roughness coefficient of 0 because there are essentially no knots or anything at all. Once you figure out the Reynolds number and the roughness coefficient, use what's called Moody diagram, which is some crazy looking graph, to graph the Reynolds number versus the roughness, and you output the friction coefficient. Let's take a look at some examples of how you'd actually do this. Before we jump into any examples, let's just discuss one more quick concept, which is the idea that you can use the head loss equation to actually calculate the pressure drop in a pipe. Now, we said before that friction head loss can never slow down the fluid or affect its velocity because of the fact you have fluid flow rate continuity, which means that the flow in must always equal the flow out. Because you can't affect velocity, the thing that does change is going to be the pressure in the pipe. We've discussed that a few times. So you're going to have your beginning pressure and your final pressure are going to be a little bit different due to the loss of energy in the pipe. And this is exactly why you would need to introduce pumps to add more pressure or energy back into the system. So using your equation for head loss, which you see you've got right here, where head loss is equal to our friction factor times L over D times V squared over 2G, change in pressure is just going to be rho G times head loss. And this should make some sense because, again, that's just our Bernoulli equation that we discussed earlier in the class, which had the base units of pressure. If we wanted to write that just a little bit differently, we could kind of combine these two equations here, and we get that the change in pressure along a pipe is equal to the following, which is our friction factor times rho V squared over 2 times the L over D. Now let's jump into an example where we solve for all of this stuff and you actually get to see where all of these concepts come into play. So in this example, we've got a conduit or a pipe with water flowing. The water is 20 degrees Celsius. We've got a Q, or flow rate, volumetric flow rate of 0.05 meters cubed per second. The pipe length is 1,000 meters. Our diameter is 0.2 meters. We're given the material, which is asphalted cast iron, and we're asked to solve for the head loss per kilometer of pipe. I think sometimes this throws students off, but essentially all we're trying to do here is take the base length of 1,000, find the head loss for that, and that means that every 1,000 meters of pipe, we're going to have this much head loss. So essentially, when we go to solve this problem, we have a couple different steps, and let's take a look at those steps now. So in these types of problems, what we're going to try and do is calculate the friction or head loss in the pipe. To do that, we're going to need a couple different things. Number one, we're going to need the Reynolds number. Number two, we're going to need the roughness coefficient. And then number three, we're going to look up the friction factor using whatever form we need, whether that is for smooth or laminar flow, or whether that's for turbulent flow. Once we've got the friction factor, we'll then go back, calculate the head loss, and if we need to, calculate any pressure drops in the pipe. So let's take a look at this example here and see what we're given, and actually calculate what we need. So to get this problem started, let's first calculate Reynolds number. We've got a number of different equations for Reynolds number that vary. We're going to write down all of them right here and try and see which one is going to be most useful to us. So what we can see in this example is we're going to need to first calculate the velocity of fluid in the pipe, because we're going to use our Reynolds equation is equal to V times d over squiggly v, or kinematic viscosity. So we were given that Q is equal to 0.05 meters cubed per second. So we're going to use our equation that Q is equal to A times V. So our velocity is going to be Q over A. What is our Q? Our Q is given to us in this problem as 0.05 meters cubed per second. What was our area? Our area was given to us as, well, we don't know, but that is going to be pi over 4 times the diameter squared. We were given that the diameter is 0.2 meters squared. And what we get is that our velocity is equal to 1.59 meters per second. To calculate the Reynolds number, we can now just plug this in and we will be able to solve. So we'll say that Reynolds number is equal to our velocity of 1.59 meters per second times our pipe diameter, which is 0.20 meters. We divide that by our kinematic viscosity, which we were actually given in our problem right here. It's 1 times 10 to the negative 6th. So when we plug everything in, you'll see that our Reynolds number is 3.18 times 10 to the 5th, which is greater than 3,000, which means that our flow is turbulent. Because our flow is turbulent, what we now are going to do is we're going to have to go to the Moody diagram. The Moody diagram requires us to have Reynolds number, which we already have, but it's also going to require to use the roughness coefficient. So our second step in this problem now is to calculate the roughness coefficient. So how do we calculate pipe roughness? In this particular question, they told us that we have asphalted cast iron as our pipe. Now we know that the roughness coefficient, Ks over D, is going to be what we need for our graph. For the particular pipe, if we look at our table for that material, asphalted cast iron, we can see that Ks, or the relative sand-tight coefficient, is equal to 0.12 millimeters. To calculate the roughness coefficient, we use this Ks over D. To calculate that, we have 0.12 millimeters divided by the diameter of the pipe, 0.2 meters. We just want to make sure those are in the same units, and everything will work out there. So our top is 0.0012 meters over our diameter of 0.2 meters. You can see that this becomes unitless. We get a Ks over D of 0.00006. Now that we've got that, what we're able to do is go to our Moody diagram to calculate the friction. Let's take a little bit of a look at how we actually do this. Let's go back to the slides. Now, the way that we're going to do that is we're going to look at this really crazy looking graph over here. Now, as you can see, along the x-axis, you have the Reynolds number. Along the y-axis on the right, you've got this Ks over D value. And you can actually see that each of the blue lines here is actually relative to one of those roughness coefficients. So in our particular example, we had Reynolds number was 3.18 times 10 to the 5th. So you can see you've got 10 to the 5th down there on the bottom. Everything to the right is multiplied by that 10 to the 5th. So we have 3.18 times 10 to the 5th. And you can see our graph is kind of hard to actually navigate. And I've put this red bar there as signaling to us that we've got somewhere in that area is 3.18 because it's not exactly clear where that value would be. I then look at the value of 0.0006 for my relative roughness coefficient, and I locate that line right there. So I'm going to try and do this as clear as possible in this form over here. But what you can see is we've got this friction coefficient right here, and that's going to lead us to this line right there. So I'm going to look at this line all the way through, and I see that there's this intersection right here. With this information, what I can see is that roughly here on the graph, and if I drew a straight line all the way over to the left, I can see that my friction factor is very close to the value of 0.02. Now the tricky thing is I can't actually see the graph. I don't have all the numbers represented on the axes. So what I actually would do is I would use a much more precise and sophisticated equation to actually get what the true value of F is, which is the equation we kind of showed earlier. Now there are online tools to do this, and you can see that when I plug in my Reynolds number and my relative roughness coefficient, it yields us a value for the friction factor of 0.0186 ... So it's pretty close to that 0.02 value we see on the graph, but a little bit more complicated to get to. On an exam, what I would actually do is give you several choices for the friction factor. So it'll be your job to essentially get close to the ballpark. And if I told you in this example the friction factor is either 0.02 or 0.05, you would go through the motions, you would look on your graph and you'd say, oh, well, my value is much closer to 0.02 than it is to 0.05, way up there on the graph. Now that we've got the friction factor, what we'll do is we'll use our equation, friction times length over diameter times v squared over 2g, and we're going to calculate the friction in the pipe. So our head loss friction factor is 0.019. We'll just round up to make it a little bit simpler. The length of our pipe is 1,000 meters. The diameter of our pipe is 0.2 meters. This allows us to cancel out the meters and have a dimensionless unit right there. Times our velocity squared, which we calculated earlier, was 1.59 meters per second. Square that term. Divide that by 2 times g, which is 9.81. And what I calculate for the head loss for a section of 1,000 meters of pipe is that the head loss is equal to 12.2 meters. And there you have it. If I wanted to calculate the pressure drop in the pipe for every 1,000 meters, remember I would just use the equation from earlier. The change in pressure along the pipe would be equal to rho times g times head loss due to friction in the pipe. If I plug those numbers in, you would see that density is roughly 1,000, gravity is roughly 10, and HF is roughly 12.2. Well, I guess it's exactly 12.2, and I would get that the change in pressure in this case would be 120,000 pascals, or approximately 1 atmosphere of pressure drop for every 1,000 meters. This is exactly why when you've got an 800-mile pipeline like the transatlantic pipeline, to add that much pressure to the pipe is going to require lots and lots of energy. So instead of using pumps, a lot of times what pipes use, and we've discussed this already, is a lot are actually gravity fed. In Iceland, the geothermal power plant is actually higher than the city of Reykjavik, and the fluid flows down almost totally for free using no pumps really, other than just the gravity of the fluid delivering it to its destination. So that is everything for our lecture in this particular topic. What we discussed today was conduit flow. And essentially everything that we talked about was entrance length, figuring out how long it takes the fluid to get into its final flow type, turbulent or laminar. And then we talked a little bit more carefully about how you calculate the friction factor in the pipe and how that's going to depend on Reynolds number and this thing called the roughness coefficient. Thanks for watching, and see you next time.